Hello children, in today's class we will be discussing about the AC generator. Children, in order to understand AC generator, we need to understand about the concept of electromagnetic induction. Of course, before that, what is a magnetic flux, then electromagnetic induction, then even we need to know about the Fleming's right hand rule. Dear children, these concepts which already we discussed in the previous class, so link is given in the description. Just go through those video, so that what will happen, you get the complete concept to understand AC generator. But children, once again, let us recall once again what is a magnetic flux. Children, magnetic flux means what? If you can take any bar magnet, for example, let us take here is a bar magnet. Around this bar magnet, what will be there? Magnetic field lines will be there. So if I can keep any surface area near to this bar magnet, then what will happen? Few field lines will pass through it. Is it clear? It's very, very important. So children, the number of magnetic field lines which are passing through a unit normal area is called magnetic flux. Which means what here? If more number of field lines are passing through a certain area, then we can say that magnetic flux is more. If a less number of magnetic field lines are passing, means less will be the magnetic flux. So regarding this only, the scientist so-called Faraday, he did an experiment and he could explain about the electromagnetic induction. So what he did, children, here? So he has taken a, what we can say, just see, I'm not going to explain in detail, just let us recall once again here. So he has taken a copper coil and he has taken a bar magnet. So, and he noticed that whenever there is a relative motion between bar magnet and coil, copper coil, and he noticed that, so there will be some magnetic flux linked with the coil changes. Children, whenever there is a change in the magnetic flux linked with the coil, there will be a induced EMF which causes induced current. This entire concept only we can call it as a electromagnetic induction. Now you may get wonder, sir, why are we recalling this electromagnetic induction right now? Yes, children. So actually today whatever we are going to learn AC generator is a completely based on electromagnetic induction. So in exam they may ask you the question, on which principle does the AC generator work? So simply you can say that it's a electromagnetic induction. Children, let us recall what is electromagnetic induction. Whenever there is a relative motion between a copper coil and a bar magnet, there will be a magnetic flux linked with the coil changes which causes induced EMF, which is the reason for the induced current. Fine. And even we need to recall about the Fleming's right hand rule. Children, what is the purpose of Fleming's right hand rule? Children, here don't get confused. Fleming's left hand rule is different. Fleming's right hand rule is different. What is the purpose of Fleming's left hand rule, children? So Fleming's left hand rule is used to find the direction of force acting on a current carrying conductor placed in a magnetic field. That is different. But see, Fleming's left hand rule is related to the electric motor, what we can say motor, DC motor. But whereas here, Fleming's right hand rule is related to the what actually? Generator. So what is the purpose of Fleming's right hand rule, children? Yes, Fleming's right hand rule is used to find the direction of induced current. So this is very important. Then only you can understand actually. Okay, now. So what does it state actually, children? So we have to stretch our central finger, forefinger, thumb finger mutually perpendicular to each other, such a way that I can repeat, such a way that thumb shows the direction of motion of conductor and forefinger shows the direction of field. Then central finger will give you the direction of induced current. So with this concept of electromagnetic induction and the Fleming's right hand rule, then we can understand. Children, again I'm telling you, if you want to understand AC generator, you must understand what is electromagnetic induction and what is Fleming's right hand rule. Children, the previous videos, links will be given in the description. You must watch in order to understand the AC generator. Okay, chalo. So let us come to the today's topic, AC generator. Children, first of all, what is the purpose of generator here? Children, generator is a device which changes mechanical energy into electrical energy. I mean, it's quite opposite to the electric motor. Children, what is a motor? The motor is a device which converts electrical energy into mechanical energy. But whereas here, generator converts mechanical energy into electrical energy. So whenever there is no power supply, in general we can go for this alternate so-called generator. Now let us see what are the main parts of the AC generator children here. So of course these two are same only, don't get confused here. So it is a situation 1, okay, and here is a 2. You can take 3, 4 also, it's not a problem. Okay, so either of one is okay. So here there are let us see the main parts here children. If you can see, there is an armature, so-called copper coil, and here is concave shaped magnets, or we also can call it the horseshoe magnets, and here is slip rings, coaxial slip rings, which means what? They are not like this children, so they will be like this, so that common axis will be there. Common axis, try to understand, means so coaxial rings, which means what here? The rings whose axis of rotation is same. Is it clear? Means through the centers, through this what we can say, let us say it is like this. Let us say my two these are the coaxial rings. My fingers, just you think that they are rings, means coaxial. Okay, na? Fine. Next here is the carbon brushes, and finally here is a load resistance, load RL. Here is a RL, load resistance. Fine here children. So comes to this is armature. Here is a copper coil which is made in the form of a rectangular in shape. It's a insulated copper wire. It's a insulated copper wire, and it is placed in between horseshoe magnets or concave shaped magnets. Here, why only concave shaped magnets, children? So here the very important thing is that concave shaped magnets provides a radial and a uniform magnetic field. It's very important. They will provide uniform magnetic field. Why uniform magnetic field is needed? So that what will happen? Same strength will be there at every point, so that the force acting will be same in the magnetic field. So I hope you know what is the uniform magnetic field. So what is uniform magnetic field? The strength means the distance between the magnetic field lines, and the strength should be unique at every point. Such a field is called actually uniform magnetic field. Is it clear? Fine. And here if you can see the electric motor children, there we have half slip rings, so-called commutators, but here what actually complete slip rings which we have. Is it clear? Fine children. And here why we need actually slip rings? So that what will happen? No, there will be a continuous contact. Means anyhow we'll discuss, just let me tell you. For example, it is there children. So this B1 is there, let us say it is the S1. It is a B1. So as a copper coil is rotating, so it will be in touch. It will be in touch. Try to understand. It will be in touch. Similarly with S2 also. Similarly with the S2 also. This second end. This is the first end, second end. If you can see, this both will be in touch with every time. Try to understand. So complete in order to provide a continuous contact. That is the reason why are we using a slip rings. Clear? Fine. Now come to this one actually. Children, in order to change, let us recall, to produce induced current children, there must be a change in magnetic flux. So which means what? Either magnet should move or copper coil should move. Children, these are the magnets, they are very heavy, huge, bigger in size, let us say that. So we cannot, so we don't have that, it's not a comfort to us to move the magnet, so it is not possible. Then how are we going to change the magnetic flux linked with the coil? Means by rotating the coil. But here who should rotate the coil? They are not like a small in size, so that sir I can rotate or you can rotate. It's not like that. They are bigger in size. For that only children, just let us recall once again hydroelectric power stations. We all know that at hydroelectric power stations, power is produced. Okay. So here what happens, children? This copper coil is mounted on one axis. Try to understand. That axis is not shown completely. Here you can see here. Okay. Okay. And here let us just look at here. For example, if I provide turbines. Now this turbine is rotated somehow. This turbine is rotated. Try to understand. If this turbine is rotated, obviously what will happen? This copper coil also rotated. That is our idea, children. So here what are we doing? This copper coil is mounted on the axis. At the end of that axis, let us say one rod, let us say that shaft type, one turbine will be there. Somehow if you can rotate the turbines, then what will happen? As this copper coil is mounted on this what we can say shaft, so as the shaft is rotating, the copper coil also rotated. So when the copper coil is rotated, current is produced. But what is happening in between? Yes, let me tell you, it's very important. Okay, so let us think, children. Here, visual. So that visuals to come to our mind actually. So we have to imagine the situation. Now let us think here is, children, this is a copper coil. Let us think, rectangular copper coil. Let us just think. It's of course visual is pad only, but let us say B, C, D is a copper coil. So let us say that it is rotating in a clockwise direction. Clockwise means what here? Clockwise means what here? Try to understand. Is it clockwise? Yeah. Means AB is coming out like this. CD is going inside like this. It is rotating. Children, try to understand. This is rotating like this. It is rotating like this. In this case, whatever situation which we are taking. So again I repeat. This AB side is coming upper direction. CD is going inside. Children, right? Again I repeat. So this point is very important to understand. Because we should know the direction of motion of the conductor and magnetic field, then only with the help of Fleming's right hand rule, we can find the induced current direction. Okay, now fine. So here, this will be coming up. Means what, this AB side is coming up, CD is going inside. Try to understand. Okay, now fine. So let me tell you here. So this is AB is coming up. So let us say the cable upside direction. This is going inside. Let us say CD is going inside. Fine. Now children, what is the direction of magnetic field? Yes, is always from north to south only. And AB is coming upward direction. CD is going downwards. Now let us use the Fleming's right hand rule in order to find direction of induced current. Children, I repeat once again. Thumb should be in the direction of motion of the conductor. Forefinger should be in the direction of field direction. Then central finger will be in the direction of, the central finger will give you the direction of induced current. For suppose children. So here, yes, if you can see here, thumb is, see, because AB is coming up, AB is coming up, so thumb is in this direction. So forefinger in the direction of field. Then my central finger is showing A to B, it is showing, children. Try to understand my central finger. So this thumb finger is in the direction of motion of the AB is coming upward direction. Towards camera AB is coming. So this thumb was showing towards. This, what we can say, forefinger north to south, field direction. Then thumb is showing A to B. So here, this is a current. So here current flow from A to B. Then in CD, yes, this is going inside. CD is going inside. Okay, like this. Look at, yes. So thumb is showing inside. Forefinger, yes, this forefinger is field only, anyhow left to right only. But by this time the central finger is showing downward direction. Central finger is showing downward direction. So here current is coming like this. Current is coming like this. So which means what? A to B, B to C, C to D. Try to understand. Very important. Yes. Now it is coming, children. So it is D. So look at here. Try understand. So it is not in touch with S1, children. It is in touch with S2. So S2 to Y. Try to understand. S2 to B2. So if you just let me write here. Let us take direction S2. S2 is in touch with B2. It is in touch with Y. So current will enter like this. Current will enter like this. Try to understand. So Y to X, again B1. Very important. Try to understand. Very important. B1, A, B, C, D. S1 is not there. S1 is not in touch. Try to understand. After B1, S1 should come, right? Yes. After B1, S1 should come. Try to understand, children. So means what? We have to see, this is a load resistance, right? In a load resistance, current is going from Y to X. Y to X, try to understand. Current is going is a Y to X. Okay, fine. And here, you may get one doubt actually. Sir, okay, it's very clear to us, but how can you say that there is change in a magnetic flux? Let me tell you the concept. One second. Children, let us recall once again, children. So field is going like this. Please try to understand. Field is going like this. North to south. It is a copper coil. It is a copper coil. Let's say it's a copper coil. Now children, if you can see here, here is a surface. Now field lines are passing. Now don't you think the more number of field lines will pass? Yes. Then flux will be more. Children, having flux is not enough. Change in magnetic flux. But as it is rotating like this, children, it is rotating. Now before, let us say 100 field lines are passing. Now like this, as it is rotating like this through 90 degrees, let us say, sir, 90 degrees. Now children, what happened here? See, how many number of field lines will pass? Less. Means here, 100 number of field lines here in this case. Now it is 0. Change will be 100 minus 0. So maximum change will be there in a magnetic flux. Try to understand. So 90 degrees. Again, as it is rotating, children, try to understand. Now the number of field lines which are passing through the coil will be increasing. Increases. Now the number of field lines which are passing through decreases. Children, you assume that you imagine a situation where field lines are like this continuously. And this copper coil is rotating. If the copper coil is like this, so more number of field lines will pass. Okay. And as it is rotating for every 90 degrees, 180, 270, 360. Means we have to see for a complete cycle. In a complete cycle, what will happen? So it is ABC will be there. Complete cycle, what will be 360 degrees? After 360 degrees, it will come in this direction, right? Means what here? In the place of AB, CD will come. In the place of CD, AB will come. Now children, here, now again it is rotating continuously. Then look at here. Here what will happen? Yes, continuously the CD is coming upward direction. Yes. And AB will go downward direction. Because it is a clockwise rotation only. Now look at here. It's a Fleming's right hand rule, right? Okay. So here thumb should be in this direction. Field is in this direction. And central finger is showing vertical upwards. Try to understand. So thumb is in this direction. Field is north to south and here. So current is, it is showing upward direction, which means what? D to C. So the direction of current will be D to C. Okay, D to C. Fine. Now in AB, how the current direction is? This AB is going now inside, right? Because it is rotating like this. Children, let me tell you. It is rotating like this. So here also, right? So now it is A. Yeah, it is like this, right? So like this. So it is going inside. So thumb should be inside. Field F should be north to south always. Then my central finger is showing downward. So current is B to A. So now current goes like this. D to C, C to B and like this. So now A to S1. So current is entering A to S1. Because try to understand here. First it is in contact with S1. So S1 to B1. Very important. S1 to B1. So B1 to X to Y now. Very important. X to Y. X to Y the current is flowing. X to Y. Y to B2. B2 to S2. Again S2 to, again circle is completed. Circle S2 to again D, C, B, A. But the very important point, if you can notice children here what is the direction of current here? Y to X. In this case, the current is flowing from in the, children try to understand, in a load resistance is very important, Y to X. But here the current is flowing here, X to Y. Which means what here? For every one cycle here, what is happening? For every 360 degrees, what is happening? The polarity will be changing. That's what we can call it as alternating current, AC current. The direction of current will be changed. Even magnet also. Children, what is the difference between AC current and DC current, children? DC current, direct current, the magnitude and the direction remains same. But whereas AC current, alternating current, right? Its direction and the magnitude will be changing continuously. Is it clear? So this is how actually. So as a will be changing. See, look at here, children. See, if you can take here is a graphical representation for. Let us say here is e.m.f. is taken an e.m.f. y-axis. Let us take a time, children. So here what is happening here for, let us say for complete cycle 0, it is 90 degrees, 180, 270, it is 360 here. So here is the maximum e.m.f. means maximum current. Here is a maximum means when there is a change, try to understand children, change we have to calculate here, very important. So alternatively, let us say it's a plus, it is a minus. Alternatively it is changing it is. So once x, y to x, next to x to y, y to x, x to y, y to x, x, y. Alternatingly the polarity will be changing continuously. That's what we can call it as a alternating current. Is it clear? Fine, children. And here this EMF, induced EMF, depends on mainly three factors. It depends on first one, it depends on the number of turns in the coil, how many turns are there. The second thing is that the surface area of the coil. The third one is what children here, rotation speed. If the coil will be rotated very fast manner and the magnetic flux also change in a fast manner, then what will happen? Induced EMF, such a way that induced current also produce in a fast manner only. So, they are the three factors on which induced EMF depends. Clear children? Yes. So, this is about the AC generator. So, in exam, they will ask you the question, what are the differences between AC generator and a DC motor? Differences they will ask children. Differences they will ask, similar. Okay, do one thing. First, let us see the similarities. Just you can recall the DC motor children. One point will be there. What is that point here? In both the cases, copper coil will be rotating in a magnetic field. That is the first similarity. The second similarity is that in both the cases, there is a conversion of energy. Yes, conversion of energy only, right? So, electric motor is electrical to mechanical. It is a mechanical to electrical. What it may be, conversion of electrical energy will be there. These are similarities. But differences, children, is very, very important. Differences. So, the first difference is actually here. So, first difference. So, here what will happen? DC motor will convert electrical energy into mechanical energy. But whereas AC generator will convert mechanical energy into electrical energy. First difference. And the second one, in a DC motor children, if you can see in a DC motor, commutators are used like this. Commutators will be there. Commutators are used C1 and C2. So called half slip rings will be there. But whereas in an AC generator, we are using slip rings. Third one here, on which principle does electric motor works children? When a current carrying rectangular copper coil is rotated in a magnetic field continuously, couple will act so that what will happen? Electrical energy converts into mechanical energy. I repeat, sorry, it's not that exactly, let me tell you. So, when a current carrying rectangular copper coil is placed in a uniform magnetic field, couple will act and it is rotated continuously. That is the principle of electric motor. So, what is the principle of AC generator children? Electromagnetic induction. Electromagnetic induction is a principle on which AC generator will work. Okay children, so here see, again I am telling you, in exam they don't ask you to explain. What are the questions can be explained, what is the AC generator, what energy change will take place, and based on the diagrams questions will be asked, and about Fleming's right hand rule, electromagnetic induction, on which principle EMF depends, induced EMF, and the differences, similarities between electric motor and DC motor and AC generator. So, these are the questions can be expected. Okay children, fine. So, in the next class, we will be discussing about the transformer. Okay children, thank you so much. All the very best.